All right, we are still in Chapter 6, moving along. We get to 6.3 now, and what we're looking at here is something called double angle and half angle identities, and we're also going to take a look at something called power reducing formulas. But really, these are just outgrowths of the previous section 6.2 of the sum and difference identities. So do you remember when we talked about adding two angles within sine? Let me see if I can go through it here. Let's say this here. Let's say we're adding two angles for sine. This is the sum formula for sine. But the question is, what happens if the two angles are actually exactly the same? What's going to happen here? Or in a sense, what we're doing is we're saying, what happens if they double? And so really this is a straight outgrowth of adding two angles, or the sum angle formulas from 6.2, but keeping the angles the exact same. Well, if that's the case, using the sum formula for sine, we get sine of x times cosine of x plus cosine of x times sine of x. Well, hold on though. Aren't those really just exactly the same then? So really, if you really got this. You got 2 sine x cosine x. All right, on the left-hand side, if you say cosine of x plus x, really, aren't you really saying this? Aren't you really saying cosine of 2x? So there's our double angle formula. If you want to double an angle for sine, all you really got to do is you go 2 multiply the sine of the original angle times cosine of the original angle. That's exactly what this says. It's going to, you multiply by 2 sine of the original angle times cosine of the original angle, and you got yourself sine of the angle that should have been doubled. All right, let's take the look of the same thing for cosine here. Cosine of 2x, break it up into two same angles, right? Cosine of x plus x. And cosine is a pretty interesting one here. So let's take a look at it. In fact, we're going to get 3 different formulas out of this as we look at it. So paying attention here as we go. All right, if that is the case, I'm going to use the sum formula for cosine, which gives us cosine of x minus sine of x times sine of x. Well, if that is the case, isn't this just going to be cosine of x times cosine of x? Isn't that just cosine squared x? And at the end here, sine times sine, that's going to be sine squared. So really what we have is we have the first formula, first formula for the double angle for cosine. Put it bold here. We're going to have 2 brackets here in just a bit here. Okay, that's the first formula. When do we use this first formula? When we know what cosine is and sine at the same time. We usually like to use this one. All right, but what happens if, remember the Pythagorean theorem identities for cosine and sine, or cosine squared, sine squared? Tell me if you guys agree here. Isn't cosine the same thing as, let's see if I can move this over on the right hand side. If I move the sine squared over to here, right? That's going to give us cosine squared x is equal to 1 minus sine squared x. And so I'm going to use this formula. I'm going to plug in a 1 minus sine squared x into the original piece here. And so let's simplify this down. So 1 minus sine x squared minus another sine x squared. I could just drop the parentheses here. And then I can combine these together. And I got myself 1 minus 2 sine squared x. Put a little box around that. That's going to be my second formula for this. All right, how do I do the third formula? Well, I do the exact other way. So instead of substituting cosine squared as 1 minus sine squared x, I'm going to substitute this as, and I think you guys can guess here what that's going to be. We're going to leave the cosine squared exactly the same, but now we have 1 minus cosine squared of x. Okay, in this case, when you drop the parentheses, you better multiply in that little negative into here. So when you do that, you get yourself a negative 1 plus cosine squared x. Combining this together, particularly the cosine squared x's. Sorry, running out of room on the slide here. We get 2 cosine squared x minus 1. So there it is. Those are 3 formulas there. So that's we did for sine, we did for cosine. You can also do this for tangent. We just won't take the time right now to do it. But if you're looking at the textbook here, this is how it should be given here. So the double angle formula for sine, we just looked at that one. The double angle formula for cosine, we just figured out all 3 of those. And I think there's a homework question that tells you how to derive this. Can you prove this yourself? All right, but I like to say sometimes this first formula isn't really the one we use quite a bit, because many times what we'll know is we'll know what the sine value is, or we'll know a cosine value. So what we tend to do is we tend to use one of these 2 formulas here. Additionally, besides the double angle formulas, you may want to just kind of quickly review the Pythagorean theorem identities that you have and their equivalent forms. It'll be sort of helpful to look at and see and think about as we go through this section. All right, so we move on to example number 1. We have cosine of theta is negative 3/5. It is in quadrant 2. And we're trying to figure out what is the sine, cosine, and tangent value of an angle that's been doubled. So notice we just know what the single value is of cosine. It's almost like saying this right here, saying that we know there's an angle here. We're going to double this angle. So let's say it was maybe like 130 degrees. So by doubling it, we're bringing it into quadrant 3. Now it's 260 degrees because that would be double, right? And then we're trying to figure out the trig functions of those. So that's, in a sense, that was what we're trying to do. We're trying to figure out the trig functions without actually having to double the angle and then find the values. In fact, we're trying to figure out the trig function without even knowing the value of the angle measurement itself. Okay, so what should we do? We are going to find the sine and tangent of that angle. Why do we need it? Because we need it for these formulas here. Remember, this one has a sine and cosine in it. This one we can probably use the cosine value of it, but tangent, we do need tangent of that angle itself to give us tangent of the doubling of that angle. So here we go. For cosine, for sine, what I can do, I can find the Pythagorean theorem again right here, right? It's the square root of 1 minus cosine squared theta. I know it is positive because it's in quadrant 1. All right, then I put the value in, simplify, and I give myself 4/5. Okay, so this is sine of theta. Tangent, since I know what sine and cosine are now, oh, there's a little blurb here that Q, it's in quadrant 2, so therefore the sine is positive. Tangent is going to be pretty easy because tangent is the ratio of sine and cosine. So since we know both, we got ourselves tangent, negative 4/3. Okay, now we're able to plug it into our double angles. And so sine of 2 theta, again, there's my formula. I already figured out these values already. This was given. And then I multiply in and done. So negative 24 over 25. Now this one, remember there's 3 different equivalent forms, right? We could have used the other one, which was 2 cosine squared theta minus 1. That's easy. Since we knew what sine was already, we figured it out already, we could have used the other formula. Any of them would have given us the exact same value, which is negative 7/25. And the last one, tangent. Okay, tangent 2 theta does require the tangent value of the original angle. That's what we did already here. Plug it in the -4/3, simplifying, and we get ourselves 24/7. Okay, then of course, could you have done this even easier? Yes, since we knew what cosine of 2 theta was, we figured out for part B, and we knew that the value for sine 2 theta, without even plugging it into here, we could have actually just used this ratio right here, right? And of course, that would have been cool. We would have got the same answer anyways, but here we're just practicing with the formula itself. So our practice problem, here it is. We get sine of x is equal to 12/13. Let's see, what quadrant are we in here? Pi/2 to pi. So can you find the exact values of sine of 2x, cosine 2x, tangent of 2x, just like the example problem here? Let's go for it. Sine of 2x, formula given. And as I look back at my original given issues here, I am given sine of x. That would have been easy. I'm missing this part over here. That's what I'm missing. I'm missing cosine of x. So that I have, that I'm missing, so let's go for it. Let's find what is cosine of x, given that sine of x is 12/13. We know we're in quadrant 2 because of the conditions upon x. And we know that y coordinate is 12, the r value is 13, and I'll let you guys do Pythagorean theorem and figure out what in the world would the x value be. Alright, setting up the x value should look something like this here. So you're squaring the 12, squaring the 13, subtracting 144 from 169 should give you a 25, and when you take the square root of that, you're just going to keep the negative value here. So it's going to be x is equal to the -5 value. All right, once you get that, we're good to go. We think pretty much we have everything we need. So notice on the example problem, they did it by means of identities. This one, I did it by means of the unit circle. Again, doesn't matter which one you choose, you're still going to wind up with the same thing. All right, let's plug it in and solve. So cosine is -5/13. All right, multiplying together gets you -120/169. So that's part A. Part B, cosine of 2x. So in this case, if I did not do part A yet, and I was just trying to do this problem here, what I'd do is I would use this formula. Because notice it's just the sine formula. And I already given sine, so I might as well use this formula. If the problem said cosine of x is 12/13, then I would have used the other formula. So again, your choice. This case, super easy. You plug in the equivalent value here, 12/13, square it, gives you 144/169. Multiply by 2. How about a 2 times 144 is 288? And making that to be 169/169. And all yours to finish up. See if you can do it before me. All right, -119/169 would be the final answer. All right, tangent of 2x. Let's go for it here. So I got the formula itself, the double angle formula is 2 tangent of x over 1 minus tangent squared x. At this point, yes, I do have to do my little unit circle again, or go back to A and figure out the value here. but we find out that it is -5 is the x value. Therefore, now I have everything I need to plug in. So tangent is going to be the y coordinate divided by the x coordinate. So 12 over -5 or -12/5. So let's go for it, plugging it in. If you haven't done so already. At this point, you do have to simplify, so go for it. Can you simplify this out? All right, hopefully that was a little bit of time for you guys to do it yourself. Simplifying out here on top, multiplying 2 and 12 make 24 negative. On the bottom, it's 144 over 25. Then at that point here, you make that into a 25 over 25. And then we subtract 25 minus 144. Gets me -119. All right, running out of room completely on this slide here, so let me use another page. Let me rewrite what I had earlier here. All right, this time, I think you've seen this before here. Let's go for it here. So the numerator stays exactly the same. The denominator makes a reciprocal. At that point, reducing what we can reduce. And multiplying everything out, negative on top, negative on the bottom is going to cancel as well. So a positive 120 over 119. All right, so this was actually also the long way to do it, because if you've done part A as well as part B already, you already know what sine of 2x and cosine of 2x is. So the little shortcut, if you really want to grab it, if you already did sine and cosine of the double angle, you could have just done this, right? Tangent of 2x. Let's see, the quotient identity is sine of 2x over cosine of 2x then. And all we're really going to do is just plug in the values for what we got for parts A and parts B. At that point, the denominators would cancel. Also, it's a negative over a negative, so we can make those into positives. And notice we're going to get the same exact thing out of this here. So, perfect. All right, now going backwards on our formulas here. So the question is, can you recognize the formula? And once you recognize the formula, can you simplify what you need to simplify with? All right, 2 cosine squared, maybe we could do this here, 2 cosine squared of x minus 1. Isn't that really the double angle formula for cosine? If that's the case, this would be just cosine of double of the original angle here. So I'm going to cosine, so it's the formula pretty much in reverse. That's what you should be looking at it. So double of theta, or double of x. And the theta is this part right here, or double of x. Cool. Well, in this case, that's easy. 2 and 12 are reduced down to a, let's see, that's going to cancel, and that's going to become a 6. And then I think we know this here, cosine of pi over 6. That is going to be, again, 30 degrees if you're still thinking about in terms of degree values here. And get yourself a root 3 over 2. So this one here, cosine squared of an angle minus sine squared of an angle. That is also the double angle formula for cosine, is that right? So doubling of 22.5. So it kind of looks like this here, cosine of 2 times 22.5. And if that's the case, that will really just be cosine of 45 degrees. And we know that cosine of 45 degrees is root 2 over 2. All right, and this one's a fun one here. So we looked at double angle formulas, And now the question is, can I keep on going? Can I triple an angle? Can I quadruple an angle? Can I just go as high as I can? Since we're able to double it, can we go further? And yes, we can go further, but the formulas get a little more complicated. So notice for sine of 3x, the formula for tripling an angle is actually 3 sine of x minus 4 sine cubed x. So notice the formulas are just a little bit different. So what we're going to do is we're going to have to prove that this is true, that tripling an angle and getting the sine value is the same thing as this equivalent form here. How do we do it? Start off on the left hand side, and eventually we want to make the right hand side equal this right here. Alright, so sine of 3x, it gives you a little solution. Sine of 3x is really going to be the addition of a 2x times x. And then can you go from here, because that's what you need to do. So the sum angle formula for sine, and again going all the way back to the sum angle formulas for sine, it's going to give us this. It's the sine of our first angle, cosine of the second angle, plus cosine of the first angle, sine of our second angle. If that's the case, let's bring this down some more. I know what sine of 2x is. That's going to be 2 sine of x cosine of x. There's that piece that comes down. And then this one kind of depends what you want to use it for. But I noticed that I have a sine x over here. So I think I might as well make this into a 1 minus 2 sine squared x. Okay, got some work here cut out for us here. First and foremost, there's 2 cosines multiplying together here. Here, there's a sine of x that's going to be distributed to the 1, also to the negative 2 sine squared x. Alright, when that happens, there's that. We've combined the cosines together, and then we distributed the sine of x to the 1, sine of x to the negative sine squared x would make it a minus 2 sine cubed x. Okay, cool. Again, we're still trying to figure out how to make this happen right here at the top. How to make this happen. Notice that everything is in terms of sine. There's a sine here, sine here. Notice on my equation, or our equation, that's a cosine. So let's change that into a sine formula. And when we do that, there it is. Now let's distribute the 2 sine of x over here. 2 sine of x to this one. And again, you may want to pause the video if you need to here, just to sort of catch up on things. Or, again, this is an example from your textbook. So you're just following along with the textbook. Alright, we got that. So now let's see if we can combine some like terms together here. So 2 sine of x, sine of x. That should make 3 sine of x. And then I got negative 2 sine cubed x. Negative 2 sine cubed x. Hey, I think I got it. There it is. I've just proven that tripling an angle and taking the sine value of it, all I got to do is I got to do this stuff right here. I got to take the original angle, take the sine of it, triple it, take the original sine of it, cool, and then cube it, multiply it by a negative 4, and then subtract from what I got earlier. All right, our problem here, practice problem number 3 is, can we verify that tripling an angle and getting the cosine value for it is this formula right here. So it's going to be taking the cosine value, taking it to the third power, multiplying by 4, subtracting 3 times the original cosine value. That's what gives us the tripling of an angle and taking the cosine of it. So let's go for it here. If you haven't done so already, we have cosine of 3x. We're going to separate those out like we did in the example problem here. So cosine of 2x plus x. And don't forget, when you do this here, this is the sum angle formula for cosine. All right, when you do that, remember it's going to be cosine of the first angle, cosine of the second, and there's a minus in the formula, so always the opposite sign of the original one here. Then it's sine of the first angle, sine of the last angle. All right. I think we know what we want to do here. We want to simplify cosine of 2x and simplify sine of 2x. And so in that case, cosine of 2x becomes 2 cosine squared x minus 1. Why am I using this formula now? It's because originally I only have cosines, so I might as well change everything that I possibly can into cosines. All right, cosine of 2x, again simplified down further to 2 cosine x, or sine x cosine x right here. All right, next thing to do, distribute the cosine of x here, and how about multiply the sines together? And so there it is, 2 cosine cubed x minus cosine x minus 2 sine squared x times cosine x. Let's see. I think the only thing I still want to get rid of is this sine squared x. I want to convert that into a cosine. And so we would do that. Pythagorean theorem identity again. Okay, in this case, kind of careful here because you have a multiplication by -2. You also have a multiplication by cosine of x on this side. Let's bring this in this way just so we have it in front where we need to be. There. Okay, now let's multiply. -2 cosine of x times 1. And -2 cosine of x times a negative cosine squared x. Running out of room here, so sorry. I had to just kind of get it to the next slide here. Okay, as you guys are doing your work here, go for it. Again, pause the video if you need to here, if you're watching the video, in order to do the work yourself. All right, so the front side remains the same. The back side is -2 cosine x times 1. That's going to be -2 cosine x. -2 cosine of x times a negative cosine squared. So let's see, negative times a negative is a positive. 2 will be a positive 2. And then it'll be the cosine to the third power at this point. All right, let's put all the like terms together. All the cosine cubes put together with a 4 in front, and then again cosines by themselves are the -3, and that is what we were trying to prove, so we have proved it. All right, next, which comes off of this whole concept of doubling an angle, is this whole concept of reducing powers. So if you have something maybe like sine to the second power, sine of x to the second power, can I reduce that so I don't have to take powers of things? That's what I'm interested in. All right, but let's develop these. It would be good to sort of just kind of quickly develop these. Let's see if we remember this. So cosine of 2x. Everybody agree this is the double angle formula for cosine? And so what I'm going to do, I'm going to just switch these around just real quickly here. One goes to one side, the other one goes to the other side. All right, notice the one stayed exactly where it was, bringing the 2 sine squared x over, bringing the cosine 2x over. Let's divide by 2 everywhere, and we get this formula here. Sine squared x is equal to 1 minus cosine 2x over 2. All right, so what have we just proved in a sense? If instead of taking powers of our sine values, all we really got to do is take the angle, double the angle, take cosine of the angle, subtract it from 1, divide by 2. Again, that may seem more difficult to do, but if you are looking at a double angle formula and a single angle, and you're still supposed to square it and you don't know what that angle is, maybe it would be a good idea to see if you can do this formula. All right, so that was the power reducing identities for sine. Let's look at the power reducing identities for cosine. So cosine 2x. So give me the double angle formula for cosine that has cosine in it. Last time we looked at the one that had sine in it. That's one formula that has both of them in it. But which one of those has the correct formula in terms of cosine? So it's this one, right? It's 2 cosine squared x minus 1. All right, what should we do here? Well, let's add 1 to both sides. So now we have, oh, a little bit too fast here. We're going to add 1 to both sides, and then we're going to divide by 2. So now we're left with here. We're left with cosine squared on this side. That's going to be 1 plus cosine 2x over 2 on the other. Again, there is your power reducing formula for cosine. Again, we'll list them in just a bit here. Just to change it around here, just so you have the cosine squared on the left, and so there it is. All right, now we have to figure out the power reducing formulas for tangent. All right, there's a long way, there's a short way, of course. And the short way is to think about the quotient identity. What is the quotient identity for tangent? Quotient identity for tangent. Tangent is sine over cosine. And since we have already done those in the last 2 slides, how about get the results from them so we can figure this out? So let's do this here. Tangent squared of x is really going to be sine squared of x over cosine squared of x. We just got those, and those are the ones that we just got or figured out. So what happens here? I think the 2's get canceled. That's about it. All right, if that's the case, equal sign, numerator is left on top, 1 minus cosine 2x on the bottom, 1 plus cosine of x. Sorry, that happened a little too fast here. I do have them listed all here. So sine squared x, cosine squared x, tangent squared x. Those are your power reducing identities. All right, let's take a look at an example where, in a sense, where is it used at first of all, and then we'll see the other one here that we look about. So write an equivalent expression for cosine to the 4th power that only contains powers of cosine and multiples of multiple angles. So instead of squaring stuff, we want to bring it down to just multiplying angles. All right, here it is. So cosine to the 4th power is not really just going to be cosine squared squared. If that's the case, then we have ourselves the identity that we just learned. So I'm going to put that in. The equivalent is 1 plus cosine 2x over 2. Then I'm going to square all this. And you may have to do this off to the side here. And we'll do a practice problem in a bit here as well. So if you square 1 plus cosine of 2x, that is going to be a binomial you're going to have to work with. On the bottom, you have yourself a 2, so 2 squared is a 4. So here's the way it works out. This little guy becomes a 4, and we sort of scoot down in front as not to bother us later. As you multiply this times itself, 1 times 1 is 1. The middle terms get doubled. There's your 2 cosine 2x. And the last term gets squared. All right, everything is all good and dandy except for this square right here, because I want everything in terms of power to the 1. So I still want to get rid of this guy. So how do I get rid of this guy? The same exact process. Except the angle already is 2x. So we're going to have to double 2x, or 4x. So bringing in the formula again, but this time now you have a 2x because you're doubling a 2x. You have a 4x now. All right, and then we're going to take this 2 and we're going to bring it underneath the 1. Take the 2, bring it under the cosine 4x, and really just becomes a multiplier here. And we distribute this 1/4 to the 1, to this one, third term, and fourth term. All right, I need like terms to put together. Yeah, I think so. 1/4 here, and a 1/8 over here. So putting those together, getting common denominators here, and eventually, how about we get ourselves a 3/8. Adding again, 2/4 is 1/2 really. So 1/2 cosine 2x, and then 1/8 cosine of 4x. All right, our problem here. Can you do the same thing for sine? Sine to the 4th power, sine of x to the 4th power. I want the formula to contain no powers of the sine function, but could contain multiple angles. All right, hopefully you went ahead of me here. I'm going to try to catch up with you here. So sine of x to the 4th power is really going to be sine squared x being squared. And we're going to use our power reducing identity here. And that changes into 1 minus cosine of 2x over 2. And let's see, we're going to square the numerator. And then let's square the denominator, but 2 times 2 is 4. That's an easy one. All right, just like the example problem here, let's move that 4 out in front so it doesn't bother us here as we do other stuff here. So move the 4 out in front, really becomes a multiplier of 1/4 as opposed to dividing by 4. And that part comes over here. All right, I'm going to have to multiply. Let's see, 1/4 is over here. That one, that's going to be a multiplier of all that. Let me do it off to the side maybe. So 1 minus cosine of 2x times another 1 minus cosine of 2x. And if that happens, then we get ourselves 1 times 1 is 1. 1 times a negative cosine of 2x is negative cosine 2x. Then there's another negative cosine, so it makes 2, negative 2 cosine 2x. And then at the end, I got myself, let's see, a negative times a negative is a positive. Cosine 2x times another cosine 2x is cosine squared 2x. Okay, so let's bring this up to the top here. All right, and everything's great except for this part right here, cosine squared. Got to reduce that down some more. So let me rewrite this here on the next slide first. All right, so there it is. It's rewritten as it was on the previous slide. And now let's use the power reducing formula for this term right here. So everything else remains the same, but now we have ourselves a 1 plus, because remember, because that's part of the formula, cosine of 4x over 2. All right, let's take this 2, put it underneath the 1, take the 2, maybe as a multiplier or underneath cosine of 4x. Give you guys catch up time here, give you guys a little time to catch up here. All right, and then let's distribute this 1/4. Distribute this 1/4 to all 4 terms, and kind of notice that there are 4 terms here. All right, gives us 1/4 minus, looks like 1/2 cosine 2x plus 1/8 plus 1/8 cosine 4x. Moving the constant terms together. The second term still stays exactly the same. The last term stays exactly the same. All right, and again, what we've done is instead of taking powers of sine, we reduced it just to multiples of our angles. I'm going to skip this problem for now. And due to time constraints here, let me finish off some other stuff. All right, now we turn our attention to the half-angle identities. And the half-angle identities really come from the power-reducing formulas. So everything just sort of builds on itself as we go here. And so as this is the this was the power-reducing formula for sine right over here. But notice the relationship between the angles. This angle is the angle, and this one here is your doubling of the angle. All right. So here's what we're going to do. We're going to say that that angle is going to be half of theta. And again, theta is just going to be some kind of random angle. So let's replace all the x's with theta divided by 2. And again, we're just sort of making up that formula. I'll give you the list of them on the next slide. All right, if that's the case, there it is. X is replaced with theta divided by 2. Let's simplify that a little more here, especially this part over here. So sine squared of theta over 2 is equal to 1 minus cosine of theta over 2. Okay, and here's what I'm going to do. I'm going to solve for sine over here. I'm going to solve for sine. So I'm going to take a square root over here. I'm going to take a square root over here as well. And then I have to put a plus or minus because depending where that angle is going to land, I have to know what that angle will be, or will that be. All right, so here it is, my formula for the half angle. So what I'm looking at is, instead of doubling my angle, what we'll really finally come to the conclusion on is what happens if I want to half the angle and find the answer. All right. A little plus or minus, if you want to write this down, the plus or minus really depends on the quadrant that theta over 2 is in. So if you're looking at an angle and you want to take half of it, you got to know where the final resting area or the terminal side of the angle is going to be at before you can make that plus or minus determination. All right, so here are the half-angle identities. We could have done the same thing for cosine, and we could have done the same thing for tangent and figured it out here. So the bottom here is somewhat important here. It says the sign of plus or minus, which is on every single one of these here, really just depends on which quadrant that theta over 2 is going to lie in. All right, so let's use this formula here. We need to find, or use the half-angle formula to find the exact value of cosine of 157.5 degrees. Now that is definitely an angle we don't know. But if we double this angle, and say, hey, 157.5, double that, that really would be 315 degrees. That angle we actually know. So we're going to use the half-angle formula using 315 degrees, or actually 315 over 2. To get what we want. So as an example, here it is, cosine 157.5 degrees really is cosine of 115 degrees over 2, and then we're going to use that half angle formula. So we're going to really, to get the half angle of cosine of that, we're just going to plug in cosine of 350 degrees, add 1 to it, divide by 2, take a square root, and that little negative sign, we're going to think about, okay, where is 157.5 degrees? That is going to be in quadrant 2. So it's going to be in quadrant 2, and we know cosine is going to be negative in quadrant 2. So therefore, we keep the negative sign out of these. All right. And what they do is technically they are taking cosine of 315 degrees. but it's going to be the exact same thing as cosine of 45 degrees. That's what the book uses. The book always brings everything back into quadrant 1 because it's pretty easy to do. So if you think back, 315 degrees would be about right here, right? And so notice it's the same exact cosine value as cosine of 45 degrees. So if you take everything back into quadrant 1, you're going to get the same exact answer. All right, keep on going here. If that is the case, then what we do is we get rid of the cosine of 45 degrees by making it a square root of 2 over 2. And the way this book does it here, kind of a little genius way to do it. Other books don't do this here. They multiply in a 2 on top and 2 on the bottom because this will make a perfect square of 4, which is kind of cool. Makes sense there. If that's the case, it also gets rid of the denominator. All right, and with that said, that's going to become a 4, so that's just going to move outside, and we get ourselves an answer. There it is. So it is a negative square root of 2 plus a square root of 2 underneath divided by 2. Your job, can you find the exact value of sine of 112.5 degrees? I'm going to do this one just a little bit different than how the book did it. All right, so all yours here. And again, we should still come up with the same answer here. Sine of 112.5 degrees really is going to be the sine of 225 degrees divided by 2. And then we're going to think about 112 degrees. That is quadrant 2. And sine value is actually positive in quadrant 2. So what we're going to do is we're going to say, okay, this is going to be the positive of, and then here's my half angle formula of cosine 225 degrees. All right, so then now the question is, what is cosine of 225 degrees? Let's start simplifying this out. And so, hopefully you did it already here. This is going to be a negative square root of 2 over 2. All right, we can simplify a little bit here. So negative and negative will make a positive, or subtracting a negative, same thing as adding. At this point, if you want to, you can multiply by 2 here, multiply by 2 here. I gotta show you this here. This is the way the older math textbooks always had this here. What you would do is you'd simplify. You would get common denominators for the top right here. So there's my 2. You would simplify the numerator. So then you get this. So 2 plus root 2 over 2. And then you still got this little 2 on the bottom. And then you would make this guy into a complex fraction. So you'd say 2 plus root 2 over 2 now multiplies 1/2. Which will then become 2 plus root 2 over 4, which then will become, because then you can simplify this out, the 4 goes out, and you're left over with square root of 2 plus square root of 2 over 2. Notice the way the book did it on the previous example, a lot easier. That multiplication by 2 inside it is a lot faster here. Anyways, just want to show you, this is the older textbooks used to have a whole bunch more steps here. Very much more involved. A lot more steps and simplifying things out slowly. All right, as an example here, let's go for it here. First things first, we're not going to do tangent of theta over 2. It's we'll save it for later. Let's just do sine, because sine is going to be at least good enough for us to sort of look at. All right, so as an example for number 7, we have sine of theta is -5/13, and then we have theta itself. It lies in quadrant 3. Okay, here's our problem. Our problem is all our half-angle formulas, they actually are in terms of cosine, not sine. So before we do anything else, we have to get this guy in terms of cosine instead of sine. So you have one of two choices. You can either do it by identity, so cosine theta then, because it's a quadrant 3, it's a negative, and you use your Pythagorean theorem to simplify, you get -12/13. All right, you can also do it by the graphic approach or geometry approach to it, right? You know that this is the y value and this is going to be the r value. And so if you do that, and you also know you're in quadrant 3, so you bring this out this way. And you do a little bit of work here. You say the y value has to be a -5, and that means the r value has to be 13, and then you have to use some Pythagorean theorem identity. I'm sorry, not an identity, the Pythagorean theorem itself. A squared plus b squared is equal to c squared, or x squared plus y squared is equal to r squared. And eventually you find out that this has to be a -12, and so hence that's why you have this. Okay, once that is done, now you have to figure out where does theta over 2 lie. And let's talk about this here, because that's not in the textbook that much. If you are in quadrant 3, you gotta think about this here, and you're going to take half of this angle. The question is, where are you going to end up? And so let's kind of just think about this here. If you are at a little bit past 180 degrees, let's say it's 181 degrees, and you take half of that, wouldn't you wind up in quadrant 2 with like 90.5? Or if you're at the tail end of quadrant 3, let's say you're at 200, not 270, but 268. And then you take half of that, wouldn't you be at 134 degrees? So notice, if the angle itself starts off in quadrant 3, half of that angle would end up in quadrant 2. Cool. So okay, that's what that is, and that allows us to put a little plus sign here. That's not really given. So the formula that we want is the one with the plus sign, because theta over 2 lies in quadrant 2. Cool. All right, with that given, we know what cosine theta is, which is -12/13. That becomes plus plus, so we're really adding, making the 1 into a 13/13 gives us 25/13. And then the books just sort of quickly goes over this here. You would take the reciprocal of 2, which is 1/2. Kind of does this real quick here on you. You get a 26 on the bottom, which is not a perfect square. On the top, you get still a 25, which is a perfect square. And then you have to multiply by square root of 26 to rationalize your denominator. So there it is, final answer. Okay, let's look to our problem. Our problem still comes from example number 7. And now we want to find cosine of theta over 2. So if we think back to example number 7, don't forget, is we learned that cosine of theta is equal to -12/13. And we were in quadrant 3. That's what we learned from the example from number 7. So let's go for it. So half angle formula for cosine, this plus or minus. And now the question is, which one do we want to choose? Well, we talked about it. Let's see, since we're in quadrant number 3, half of that would be in quadrant number 2. So we're going to choose the negative value of it because cosine is negative in quadrant number 2. All right, and putting this all together, cosine value was negative 12 over 13. So plugging that in. And the rest of it really is just simplification, really. That's kind of what's going to happen here. And so let's make that 1 into a common denominator. 13 over 13. Still keeping that little negative on the outside. 13 minus 12 is a 1. Now let's do this here. Let's just multiply by the reciprocals here. So this 2 really is 2 over 1. So equal to negative of 1/13 times 1/2. All right, multiplying that out would give us the square root of, or negative square root of 1/26. And let's do this here. Let's split these off into 2 different pieces here. So how about a square root of negative 1 on top, square root of 26 on the bottom, and of course square root of 1 is just going to be a 1. And can't keep that denominator with the square root of 26, so therefore we have to rationalize it by multiplying by square root of 26 on both top and bottom. And eventually we end up with a negative square root of 26 over 26. All right, I know there's been a lot of formulas here. A lot of formulas to deal with, especially in this section, the double angle formulas, the power reducing formulas, the half angle formulas. Okay, so again, hopefully this is going to go in a 3x5 card somewhere for you so that you can sort of be mindful of those, and unless you really want to memorize these. Okay. One last problem to go, and this is an identity. Again, a little bit tougher identity. It's sine of x over 2 times sine of x. And the question is that the same, or can you verify that it is the same as cosine of x over 2 multiplied by 1 minus cosine of x? So there's, I've got to get this here. And so I want to just share you a little bit with my struggle here on this here. This is my first attempt. My first attempt was to see if I can work with the sine of x over 2, the half angle formula for sine. And when I did that, I went to here, and my only problem was, my question mark here, was the fact that I do have a plus or a minus. Is that going to affect me any? And so then I said, okay, forget this. I'm stopping here. How about if I go from the right-hand side, half angle formula for cosine, and that's not going to work. So my first attempt failed miserably. I did not know how to do this. How do I get this guy to look like this guy, or this guy to go backwards to this guy, or somehow meet in the middle by simplifying here? So first attempt failed. So I'm thinking, okay, that's not going to work. So then I started my second attempt. All right, my second attempt again was this sine of x over 2, because I'm thinking, okay, somehow this has to work out. So as I did that, here's my fun stuff here. I really couldn't quite see how that's going to happen. So the 1/2 goes on the outside, and then if you do this here, this all works out not so nicely. And so it was gibberish. And actually looking at it, actually having a little bit of a frustration here, I finally stumbled on, like, oh, that's what it is. So here we go. So I figured finally out I'm going to go from the left-hand side, I'm going to move over to the right-hand side, and this is the way I'm going to do it. And so I looked at this, saying I'm going to leave that sine of x over 2 alone for just a little bit here. And I know that if I double sine, my double angle formula for sine looks like this. But what happens if this little sine of x, that is already going to be my double angle formula. So if this is x, this is 2x, that means these guys would be x over 2. It's almost like the half angle of each of those angles here. And so I'm going to change this sine of x into this 2 sine of x over 2 times cosine over 2. And there it is. It was this little piece I did not see yet when I was doing this. All right, moving on. Moving things around. Putting the sine of x over 2 and another sine of x over 2 together. Now it's sine squared of x over 2. And then I knew I liked this in front, cosine of x over 2. That was already good in front because that's exactly what I'm trying to do. So I'm going to move this out to the front, move this little 2 into the middle. And so this part I like. And now I need to transform this, again looking at what the end that I wanted in mind. I want this to be a 1 minus cosine of x. Somehow. Don't even know, but let's see. Okay. So I decided to separate that 2 out, just so I can really focus on this sine squared of x over 2. All right, then I figured I should probably use my power reducing formula right here. Power reducing formula. I did it. It was, remember, don't you forget, you double this formula, right? So because of that, we're going to actually double this. So doubling a half actually cancelled off the 2's here, and of course, this little 2 here and this little 2 here. So now we have the x like I wanted it. Now the 2's cancel right there, and then I'm actually left exactly with the right hand side. So it took me 3 attempts, probably a nice 15 minutes or 10 minutes trying to figure out how to do this here. Got stumped, was going sort of the wrong direction. That's exactly what happens with these identities, because you sort of look at it like, that's not the direction I want to go. So eventually you solve it here. So I give myself a yes, I did it. All right, because some of these are kind of tough.